Ever wondered how your devices stay connected as you move around a large building? Or why your Wi-Fi network can handle multiple devices without crashing? The secret lies in wireless LAN topologies like BSS, ESS, and IBSS. In this video, I'll break down how these systems work, why access points are crucial, and how they keep your network stable and scalable. Whether you're a networking newbie or a tech enthusiast, you'll walk away with a clear understanding of wireless networks. Ready to unlock the secrets of seamless connectivity? Let's dive in. To function properly in half-duplex, the solution is to have a closed area in which we will have several mobile devices forming a round of a fixed device. In this scheme, when one of the laptops wants to participate in the communication, it will have to announce itself, or introduce itself, and wait to be authorized to do so. The 802.11 standard calls this process Basic Service Set, better known by the initials BSS. At the heart of each BSS is a wireless access point, also known as an access point, which bears the initials of AP. The AP operates in infrastructure mode, which allows the infrastructure of a wireless network to be formed. The PA and the members of the BSS must all use the same channel to be able to communicate with each other. Since the BSS depends on the AP, it is delimited by the area where the signal from the AP is usable. This area bears the initials BSA for Basic Service Area. It can be seen as a cell or an area. In the diagram, the BSA, or the cell, are represented by the gray circular area, which centers around the access point, i.e. the AP. The AP serves as a single point of contact for each device that wants to use the BSS. It advertises the existence of the BSS so that devices can find it and try to join. To do this, it uses a unique BSS identifier based on the AP's own MAC address. This is called BSSID. The AP also advertises the wireless network with an identifier. This is called the SSID. It is a text string that contains the name of the Wi-Fi. The BSS ID can be thought of as a machine-readable name tag to identify the access point, and the SSID as a human-readable name tag that identifies the wireless service. When a device associates with the BSS, that membership is called an association. The wireless device must send a pairing request to the AP, and the AP must or accept, or refuse demand. Once associated, the device becomes a client or a station of the BSS. As long as the wireless client remains associated with the BSS, communications to and from the must systematically go through the PA. It is by using the BSS ID as a source or destination address that data frames can be relayed from the AP or to the AP. So, one might ask, why does all customer traffic have to pass through the AP? Or, why can't two customers simply communicate directly with each other without going through the AP? Well, that's because if customers are allowed to communicate directly, then there would be no need for BSS. The fact that the data passes through the AP keeps the BSS under control and stable. It should be kept in mind that even though the data is supposed to pass through an access point, and many other devices, being part of the same area, can listen to the same channel and therefore hear the transmissions. Unlike data that circulates in an Ethernet cable, here the data is accessible by air to all the people who happen to be carrying. If the frames are not encrypted, anyone can inspect their contents. The AP and its associated clients form an autonomous network, but the role of the PA at the center of the BSS is not limited to the management of the BSS, because sooner or later, wireless customers will have to communicate with other devices that are not members of the BSS. Having both wireless and wired capabilities, the access point can establish an uplink cable to an Ethernet network. The 802.11 standard will call this Wired Ethernet Network, a distribution system for wireless BSS, as can be seen in the diagram. You can think of an AP as a translator, which translates frames from two different media, wireless and wired, before moving up to layer 2. In other words, the AP is in charge of mapping from a VLAN to an SSID. On the diagram, the AP maps VLAN 10 to the wireless LAN using the My Wi-Fi Network SSID. With this representation, we can think that the clients associated with the SSID of My Wi-Fi Network are connected to VLAN 10. This concept can be extended so that multiple VLANs are mapped to multiple SSIDs, as shown in this diagram. To do this, the AP must be connected to the switch by HASH, a trunk link that allows VLANs to be transported. In the diagram, VLANs 10, 20, and 30 are connected to the AP by the DS, which is the distribution system. APs use the 802.1Q tag to map VLAN numbers to their SSIDs. Like what? VLAN 10 is mapped to the My Wi-Fi Network SSID. VLAN 20 is mapped to the neighbor SSID. And VLAN 30 to the SSID guest. The schema you see actually represents a single AP that uses multiple SSIDs. Customers must use the appropriate SSID, which has been mapped to the respective VLAN, when configuring the AP. So here, the AP appears as multiple logical APs, one per BSS, with a unique BSS ID for each. On Cisco access points, this differentiation is typically accomplished by incrementing the last digit of the radio MAC address for each SSID. That's why we see a series of numbers at the end of the BSS ID. So, while an access point can advertise and support multiple logical wireless networks, each SSID covers the same geographic area because the PA uses the same issuer, the same receiver, the same antennas, and channels for each SSID it supports. Now we're going to talk about ESS, which is Extended Service Set. An access point cannot cover the entire area of a large building. To increase the coverage limited by the access point, simply add more APs and distribute them geographically. When access points are placed in different geographic locations, they can all be interconnected by a switched infrastructure. The 802.11 standard calls this process an extensive set of services, which can be found under the initials of ESS. The idea is to combine several access points so that the wireless network is completely transparent to the user. Ideally, the SSID, which is set on the different APs, should be identical, because otherwise, the customer will have to reconfigure the Wi-Fi each time he moves from one area to another. On the diagram, we see that each zone has a unique BSS ID, but shares the same SSID. For example, in this configuration, a client that is in the BSS1 area will be able to connect to the AP1, and if it moves to the BSS2 area, then it will automatically hook the AP2. This is called homelessness. It should be kept in mind that each AP offers its own BSS on its own channel in order to avoid interference between APs. When a device moves from one access point to another, it scans the available channels to find a new access point and, therefore, a new BSS. The device roams from BSS to BSS and channel to channel. Typically, a wireless network uses access points for better control, better organization of its architecture, and for scalability reasons. But sometimes, this is not necessarily possible or practical depending on several situations. For example, two people want to exchange documents during a meeting, without needing to request network access. Or even a user would like to print documents on their personal printer without necessarily depending on an access point. The 802.111 standard allows 2 or more wireless clients to communicate directly with each other without any network connectivity. This is called an ad hoc wireless network. It is also called Ensemble de services de base, de services de indépendants in French, which is found under the initials IBSS. For this to work, one of the devices must take the lead and start publishing a network name with radio parameters, a bit like an access point would. Any other device will then be able to join the network. IBSS is still quite limited and can become unstable beyond 8 to 10 connected devices.